Good day and welcome back for the third part of our discussion on integrating rational functions. In our previous discussions, we reminded ourselves of how to come up with a partial fraction decomposition for a proper rational function. In this video, we want to focus in on the case of having an improper rational function. And let me just remind you what those terms mean. A rational function is a polynomial over a polynomial, and the rational function is proper if the degree in the top is smaller than the degree in the bottom. So I had a small typo on the note handout. And in this case of having a proper rational function, as long as we can factor the denominator into linear and irreducible quadratic terms, we can immediately write out the form of the PFD. And as a reminder, each and every factor corresponds to a term in the PFD. So in this case, there would be 4 terms in the PFD. 1 for x plus 1, 1 for x minus 3, 1 for x minus 3 squared, and 1 for the irreducible quadratic. Writing this out, we have the x plus 1 term, a term corresponding to x minus 3, a term corresponding to x minus 3 squared, and a 4th term corresponding to x squared plus 4. And then we balance these out appropriately with constants. A single constant paired up with each term coming from something linear. So even if it's a linear term raised to a power, it's still just a single constant. And for any irreducible quadratic, we need a constant x plus another constant above it. And note, if x squared plus 4 happened to be squared or raised to a different power, then we would be adding on even more terms to the end of the partial fraction decomposition. And remember, the main reason we are interested in the partial fraction decomposition is that once we've expressed the function in this simpler form, it becomes significantly easier for us to integrate. So a partial fraction decomposition is an algebraic tool to help us write a function in a form that's more conducive to integration. Now let's explore the case of having an improper rational function. That is a rational function where the degree in the top is larger than or equal to the degree in the bottom. Whenever this happens, what we are going to have to do is perform a polynomial long division to rewrite our function. So in this case, we are going to have to divide x squared plus 4x plus 3 into x cubed. And I know it may seem like it's been a while since we've done polynomial division, so quick reminder, if you want to divide numbers, say 3 into 10, you ask yourself a simple question. 3 goes into 10 how many times? And it goes into 10 3 times. Then we subtract away what we get when we multiply those two numbers together. And once we get down to this point where it does not go into the number, we're done. This 1 is our remainder. Algebraically, what this is telling us is 3 times 3 plus 1 is 10. And we will make use of this idea in a moment. For now, with our polynomial division, the only difference is we focus on the leading or largest term. We ask ourselves, x squared multiplied by what gives us x cubed? And the answer is x. Then we subtract away the product of x with our polynomial. So we'd be subtracting away x cubed plus 4x squared plus 3x. And be careful to distribute the negative sign through. A common mistake is to forget to do that. X cubed minus x cubed is 0. Then we have a minus 4x squared minus 3x. And we keep playing this game. We ask ourselves once again, how many times does x squared go into minus 4x squared? And the answer is minus 4. And now we subtract away minus 4 multiplied by x squared plus 4x plus 3. So we'll be subtracting away a minus 4x squared minus 16x minus 12. So the minus 4x squared minus 4x squared cancel each other. And remember, once again, distribute the minus sign through. So the next x term would be minus 3x plus 16x. So that would be a 13x, and then minus a minus plus 12. And note, we're in this position we indicated to the right. X squared no longer goes into 13x, i.e. its degree is smaller than 2. So x minus 4 times x squared plus 4x plus 3 plus the remainder term, that is this thing we ended up with at the bottom, is all equal to x cubed. And note, this is just the first step. What we want to do is rewrite our function. And how we can get x cubed over x squared plus 4x plus 3 is the x cubed we have on the right is the numerator of this desired fraction. So we simply divide each and every term by x squared plus 4x plus 3. So we'll divide every term on the left and the right by x squared plus 4x plus 3. And note, this is going to give us precisely what we want. The x cubed over x squared plus 4x plus 3, which we have all by itself on the right, is equal to x minus 4, that first term on the left, plus the proper rational function 13x plus 12 divided by x squared plus 4x plus 3. So note, as desired, we've expressed this improper rational function as the sum of a polynomial and a proper rational function. And anytime we want to integrate an improper rational function, this algebra is going to be our first step. And this example will give you a nice template that you can follow. So keep that in mind. And we've answered the question, but I know we all enjoy mathematics and we love integrating. So just for fun, let's go ahead and use this work that we've done to integrate this function f of x. So creating just a little bit of space, if we wanted to evaluate the integral of x cubed over x squared plus 4x plus 3, we would just integrate the two functions that we have above. That would require us to integrate x minus 4, and then to integrate this proper rational function. And note, if we want to integrate that proper rational function, what we are going to need is a partial fraction decomposition. So 13x plus 12, and if we factor the bottom, it would be x plus 1 times x plus 3. And since the denominator factors into two linear terms, the PFD will contain two terms and two constants. The form is a over x plus 1 plus b over x plus 3. And I'm not going to go through all of the algebra to solve for a and b. I'm going to leave those details to you. But if you solve for a and b, you will find a is minus 1/2 and b is 27/2. And with that in mind, we now need to integrate the function minus 1/2 over x plus 1 plus 27/2 over x plus 3. And as a reminder, not all of our values for these constants, a, b, c, d, however many there might be in the PFD, do not have to be whole numbers. They can certainly be fractions. Now working left to right anti-differentiating, we have 1/2 x squared minus 4x from the first integral. And then term by term in the second integral, we would have minus 1/2 natural log absolute value of x plus 1 plus 27/2 natural log of x plus 3. And because it's an indefinite integral, we have a plus c. Also, based upon kind of a common question I will usually get from students at this point, I want to make an observation in terms of anti-differentiating. If you are going to anti-differentiate, let me just say a general constant like a, divide it by x plus b, where a and b are just constants, the big A pulls out front and you would have natural log of absolute value of x plus b, and this would be regardless of the value of b. It could be positive or negative. But the thing we need to be careful of is if we have a constant in front of that x in the denominator, then we would have to have big A pulls out front, but then it would be 1 over a natural log of ax plus b plus a constant of integration. So the term to be careful of is if there's this extra a in the denominator. And where the 1 over a out front comes from is using a substitution, u equals ax plus b. And that completes our current discussion. And if you flip to the next page in your note sheet, you can see a rather involved looking integral of a rational function. That's where we'll pick up in our next video. So stay tuned and take care.